This is a dehumidifier. Its job is to remove water from the air, so naturally I decided to turn it into a plant pot that waters itself, which is either elegant symmetry or a sign I should go outside more. The idea in theory is simple. I travel a fair bit, which means any plant left in my care is sometimes participating in a low-stakes survival experiment. So the goal here is to build something that can keep itself watered for long enough that my neglect starts to look intentional. The first step is to disassemble the existing dehumidifier and remove the functional components, such as the fan, heat sinks, control circuitry, and the evaporator coil. In the case of this product, these components are all integrated into a single removable assembly. As you can see from months of use, the PCB has been quite badly oxidized. The dehumidifier is quite easy to disassemble. Using only an electric screwdriver, the whole process took me around 10 minutes. As you can see, beneath the two halves of the outer casing, there is an assembly that contains all of the functional parts, which can be removed in one piece without too much hassle. The oxidization on the PCB is nothing a bit of isopropyl alcohol can't fix. Once everything was disassembled, I did a quick test to ensure that the functional parts were still indeed functional. With the outer casing removed, I discovered that the unit uses a form of induction control instead of a mechanical push button in order to turn it on and off again. Right on to the redesign phase. The first thing I did here was to quickly sketch the front and side elevations of the part I would be reusing. I then took the key dimensions from the part and added these to the sketch. Doing this allows me to quickly reproduce the part in CAD with the key dimensions in order to be able to design the new product around it. I then created the new enclosure for the existing functional component assembly, which was very simple. This design allowed the existing assembly to be dropped into the top of the new enclosure without the need for additional fastening. Next, I went on to design a base which serves as a water reservoir. The idea is that this reservoir base is shared with the plant pot, meaning the water which is deposited in the reservoir by the dehumidifier can be taken up by the plants as they grow. There was a little bit of trial and error involved here, but I think the eventual outcome worked well. I then moved on to the design of the plant pot itself. This is situated next to the dehumidifier, sharing the same water reservoir. The shape tries to take advantage of the rest of the unused space above the reservoir. I also wanted to make sure that everything would fit into a footprint that would not exceed my 3D printer's build plate area. As is common practice for any product designer using CAD, I spun the model around endlessly until I convinced myself that it was looking good so far. Last step, design a top cover for the top of the functional electronics assembly. Then it was time to 3D print everything and see how it all fits together. I love Bambulab 3D printers. Using all three at my disposal, I managed to get the entire assembly printed in under 7 hours. I wanted to prevent the PCB oxidizing again due to moisture. After considering a few more complicated options like additional 3D printed PCB enclosures, I decided the easiest thing to do is to use a hot glue gun to cover it with melted glue, sealing the PCB beneath the glue. After hours of 3D printing, the exciting moment had finally arrived. I dropped the existing functional component assembly into the top of the new printed dehumidifier enclosure, which, to my surprise, actually fit perfectly. I had designed a small lip in the top of the enclosure to seat the assembly securely in place, along with the additional holes on the bottom for the water to drip and, on the side, for the 12-volt DC barrel jack connection. There are slots in the side of the dehumidifier enclosure for air inlets. Air is then pushed out of the top of the enclosure through a series of radial slots I placed on the top cover. The top cover pops onto the existing functional component assembly using a friction fit. Fortunately, the inductive nature of the buttons, which use spring-shaped electrical contacts, made this design process very easy. I positioned the inductor spring contacts under the top cover, which was thin enough to facilitate interaction via skin contact through the 3D printed material of the top cover. Both the new dehumidifier assembly as well as the plant pot fit snugly into the top of the shared water reservoir. The light emitted by the control PCB can be seen shining through the white 3D printed material. The lights can be cycled and switched on or off by simply tapping the top of the device. Everything is now assembled. However, you may have been wondering how the water gets from the reservoir back up to the plant pot. This will be achieved using wicking. This is a common passive method for self-watering plants where moisture moves from the reservoir up into the plant pot via a wicking rope using a capillary action. This basically pulls water upwards as the soil dries out, keeping the soil consistently moist without overwatering it since the plant effectively draws only what it needs. In the case of my design, I have 4 separate wicking ropes which pass through the bottom of the plant pot into the water reservoir. To gain an understanding of how much water is produced from the air on average, the first step is to weigh the device without any water to get its dry mass. This came out to 819 grams. I then left the device running for 24 hours, after which I weighed it again. By this time, it's weighed 861 grams, meaning it had gained 42 grams, which translates into 42 milliliters of water gained in a 24-hour window in a room with roughly 50% humidity. For a better average measurement, I left it on for 7 days, and by that time, it was up to a total weight of 912 grams, meaning the total gain in mass over 7 days was only 93 grams, or in other words, 93 milliliters. Time to get straight into a real test. I bought a discounted basil plant from my local Aldi. I have never been able to keep this stuff alive even when I'm at home. Let's see if technology is the solution here or not. I filled the plant pot with some soil and then placed the supermarket basil plant in there to see how it gets on over the course of a week or so. I also set up a Raspberry Pi with an HQ lens in order to capture a time lapse of the eventual life or death of this basil plant. I really hope you enjoyed this video. Be sure to tune in for part 2 and to find out how the basil plant has fared and whether it's worth making one of these for yourself. I'll be releasing all of the STL files for the system along with part 2 of this video, so be sure to catch it if you want to have a go of making one at home. Thanks again for watching, and I'll see you all again for part 2.